Hello everyone. Welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. We appreciate you joining us today. Today the topic is the arc flash hazard report and calculation values in EasyPower. And as we are in the habit of doing, we'd like to start with poll questions. So if you would please help us out by participating in the following. So the first question is, have you conducted arc flash calculations using the 1584-2002 model? Again, there's no liability or no downside, strictly just understanding the perspective of the audience. And so appreciate you helping us out. For those of you that haven't joined us before, we do provide an attendance certificate verifying the time that you attended the webinar today. A lot of folks use that to support their EAU requirements. So it looks like we have a quorum on this question. Let's see how folks have responded. So we have a good mix of people that have been around a while and people haven't, I think is what this interpret from this. So thank you. Next question is, have you calculated arc flash incident energy and arc flash boundary using the Ralph-Lee equations? Again, this is something of a probe as far as how long you've been doing this, because Ralph-Lee was the original, I don't want to say founder, the original explorer of the arc flash phenomena. And so we actually owe a lot of gratitude to the guy's work and the information he shared with us all. So it looks like we're close to a quorum. Let's give this another 5 seconds. Thank you. All right. That makes sense. And then the last question, are there occasions where you need to calculate arc flash for a high tension wire or a high voltage system that's concerned about single line to ground arcs or faults? And this is a foreshadowing. All of this is available in EasyPower, and we'll be touching on it as we go through the discussion. Okay. Again, thank you for participating. Here's how folks have weighed in on this. Fair enough. Always like the maybe responses. Okay, so when I first conceived this title, this webinar, I was expecting to combine both short circuit development and explanations along with it. But along the way, or trying to develop it, I realized it was a much more dense proposition. And so look for that as a near future webinar, specifically deep diving into short circuit calculations on their own. Today, what we're going to do is talk about the major parameters of 1584 2018 version, demonstrate EasyPower features on how to display and report parameters that are included or affected, how to be able to do some modifications and some what-if type of questions, and potentially better understand or improve your analysis or use of the tools. I want to emphasize this is not a procedure presentation. This is not a lecture. The intent is to be a discussion of the capabilities of the tool and hopefully share with you some of that knowledge that I use to help folks out when we're doing arc flash calculations. Now, just as an aside, for all new EasyPower users, we provide a 1-hour, what we call a power start session, where we go through the procedures to do an arc flash study using the tools. And the intent is to get new users up and running fairly quickly. So if you fall into that category and we haven't done a power start with you, you should make that request of your sales or me. So anyway, so this is not that type of a discussion. And the whole discussion, in fact, when it was first released, 2018 version, there was a lot of discussion trying to compare the results between the old standard and the new standard. And frankly, I believe that's a fool's errand in that there's so much difference between the two. It's I wouldn't say worthless, but it's not time well spent trying to compare. It's better, I think, spent on understanding how these new features of these new parameters affect the results on my system. So just real quickly, in both 1584 and NFPA 70E, there's a section regarding terminology or definitions. And so I just wanted to touch on that topic briefly. Basically, bolted fault current is the total available symmetrical current, RMS symmetrical current, that's passed to the arc flash calculator, if you will, from the short circuit module in EasyPower. And from that, there's a number of variables that are calculated that are used in the subsequent arc flash calculations. Another element that's affected by these manipulations is the time and the recognition that the current in a shorted fault or an arcing fault can change over time and affect the trip time or response time of overcurrent protective devices. So some of that gives us pause as far as how and whether or not it's even affecting our calculations and how we deal with that. Some other terms, again, the available short circuit current is the three-phase maximum current that will occur at any bus during a shorted fault or a zero impedance fault. And so that's the basis, frankly, for the whole 1584 model. Now, ironically, or what sets it apart from the Ralph-Lee equations, is that Ralph-Lee doesn't use the arcing current in his calculations. He uses bolted fault current and doesn't consider the electrical and thermal properties and the influence of the plasma itself, which makes the calculations for arc flash results a bit more conservative if we're using the Ralph-Lee model. Likewise, in EasyPower, when the standard says that we should consider each mode of operation, in EasyPower that's defined as a scenario, and it can affect the max fault current and the worst case mode. So again, what you'll see when we get into short circuit is the need to verify whether or not there's equipment duty violations in different scenarios that we may be using in our operations. And they could actually be different than the buses or the equipment that is sensitive to arc flash because of the arc flash paradox. Then the arcing fault current is the current that's flowing through the arc plasma. Just by definition, it will be less than the bolted fault current. So again, the worst case current is always going to be the bolted fault current, and arcing current will be something less. You'll see in the evolution of the standard, actually originating in 2002, that there's a recognition by the variability, either due to thermal properties or electrical properties. There can be variation in the test data that's taken on arcing current. And especially at low voltages, the arcing current can be as much as 15% less in some cases. And so it has evolved as a definition of the term reduced arcing current. And you'll see that has some correction factors in the current equation where it didn't have in the original standard of 2002. So comparing the two, 2002 basically had two equations for voltages in the range of 208 to 1K, and then for anything greater than 1 kilovolt. And that was it. There was some adjustment for reduced arcing current. Again, that was manually applied percentage-wise. And then as a result, it recalculated the incident energy, and the tool would take whichever would be more conservative as a result, meaning the higher incident energy. Well, in 2018, there's now 3 equations, 600 volts based on 600 volt data, 2700 volt data, and 14.3. And then the results are interpolated for the actual voltage on the bus that I'm trying to analyze. And then the same process is taken to develop what the arcing current, reduced arcing current is. And this is done in the equations themselves. And then the process of calculating and reinterpolating using reduced arcing current is done. And then at that point, the correction factors are applied. I guess the whole point of this slide is just to illustrate how complicated the 2018 version is. And again, it's not all that useful to compare the results from the two, when really what we need to understand is how to better manipulate or better utilize the 2018 standard. So if I can find my mouse, we'll be in good shape. So enclosure size is one of the parameters that's been extended. Originally, it was a distance factor that was included in the original model. In the 2018 version, it's been explored into the dimensions of the enclosure, both height, width, and depth. So the standard gives us typical values for different types of gear and different voltage ranges. And then the tool will give us the ability, based upon our system being different in any one of these dimensions, to make the modification and see whether it affects the results. Enclosure size has an effect on the incident energy, pretty much like this plot here, which shows less on high voltage or medium voltage applications, less than a 20 by 20 box. There's the worst case amplification of incident energy versus open air incident energy. And then that reduces up to the point of a 49 by 49 dimension, and then it levels off and there's no reduction. And so it's a fixed amplification. The ironic thing is that at low voltage, that actually starts to reduce the amplification the smaller we get in the depth. And it's a little tough to explain this other than it becomes more of a panel projection rather than an amplified reflection. So that requires more discussion to really understand what we're doing. Electrode gap is another element that's been reconsidered from the original model. Now we have 2 ranges for electrode gap. For the low voltage equations, the range is 635 to 76.2. And then for the medium voltage, it's 1905 to 254. And again, the standard gives us typical values, and we can modify these if we think it's necessary, if it's going to help our calculations. Electrode configurations. Now this received a lot of buzz and a lot of discussion when it first was published. And what it amounted to is that the original standard had enclosed calculations and then open air calculations for the incident energy. And we've defined 3 enclosed configurations and then 2 open air configurations. And they have varying degrees, again, of effect or amplification for various reasons. The most hazardous, if you will, is the horizontal in a closed box. Then vertical in the closed box is similar to what was originally studied in the original equations. And then vertical in a closed box, this should be VCBB. Vertical in a closed box, I take that back. The center one is vertical in a closed box terminated in a barrier. So it's the mid-range, and vertical in a closed box is the least amplification or the least hazardous. Just a real quick point. Again, this is something that's been covered ad nauseum, but this is the example of vertical in a closed box, vertical terminated in a barrier in a closed box, and horizontal in a closed box. And the issue is where the plasma blooms or spreads out. Tests have shown that if an arc forms on this bus work, it travels to the end of the butt, the butt end of the conductors themselves, and then blooms down. In a vertical terminated in a barrier, it can start and travel down, but then it blooms out horizontally, and that's where you get more of an amplification of the hazard. And then the worst case is horizontal in a closed box, where you're staring right at the butt end of the buswork, and worst case, a technician would receive the full effect of the bloom. Now, what's interesting is that this orientation, although it looks like it's horizontal, actually would be defined as a vertical in a closed box because the terminals don't point out at the technician doing the work. And I think that's something of a surprise to some of us. Okay, and then open air configuration. It's the same kind of thing where horizontal in open air is the butt end of the bus work or the terminals is staring right at me, whereas vertical in an open air, I'm standing to the side and the bloom is actually down and away from me individually or personally. Reduced arcing current, as I mentioned before, it was included in the original standard 2002, and it was manually entered. The suggestion was to start with 85%, and it only was valid up to 1,000 volts. Well, in future tests, it was determined that the reduced arcing current phenomena was in effect all the way through the whole range of the 2008 to 15,000 volts, but it changed according to the voltage, and consequently it's included in the equations now, not in the manual entry. Now, time is affected by all these potential amplification factors as far as the voltage fault current. So anything that changes voltage fault current potentially has the ability to change our response time. And so now we have the admonition to consider motor contribution, potentially take into account loads or sources that may change, and then their potential for low current sources never to drop off during the whole life of the arc, which complicate the whole discussion. And so we'll touch on that briefly, but this is more of a low voltage situation. And he says that without regard to what's going to be shown as a result, as an example. So here's a summation of the calculation steps. First of all, you have to determine the average arcing current by calculating using the three equations for the different voltages. Then you define a final arcing current by interpolating for the voltage that you're using. Then you just decide the correction factor for the size, which is going to affect our intermediate incident energy. Then the final energy was determined by interpolating the three voltages. Then we have to see how it affects the arc flash boundary by calculating our reduced arcing current, and then make adjustments to the arcing current and go back and recalculate and reinterpolate the incident energy as a result. And all this affects the arc flash boundary and the incident energy. So it's non-trivial, and there's the intersection of the ability to do multiple correction factors. Now, this includes the class of the equipment, the voltage, the air gap, the electrode configuration. And these are built in, as you'll see, in input that the operator can make in the EasyPower adjustments. But then in addition, there's manual adjustments to be able to use either the typical value that come out of the standard or specific values for any of these variables. Then there's the ability to verify that at less than 240 volts and less than 2000 amps bolted fault current, there's a likelihood that an arc will not sustain, and consequently we can limit our concern about hazards in this category. Likewise, if there's long trip times if there's high incident energy because of long trip times, the standard says it may be reasonable to limit our calculation time to 2 seconds, emphasizing the ability to escape if an arc flash occurs, and to ensure that we're using engineering judgment. So this is, kind of puts it on us whether or not we apply the 2-second rule. There's a concern or a suggestion that we want to compare, including them. I take it back. There's a concern that if there's not an arc barrier between the incoming conductors on a main breaker and the main bus that breaker's protecting, then we have to exclude it. We can't count on that for calculations. And then there's a suggestion that we have a dynamic assessment of arcing current, which means that we consider long arcs to have a reduced current and consequently lower incident energy as a result. And then having scenarios that compare different configurations of our system based upon potential operations that require maintenance in that condition. Let me just take a second and see what we got. Some questions coming in, and I'm not sure I'm going to cover them all. So Carlos is asking, may we use the arc flash calculator 1584 for DC? The answer is no. IEEE 1584 specifically does not cover DC, but with that said, EasyPower does have the ability to analyze DC arc flash using the max power method, and I'll touch on that as we get into the examples. Available fault current in the utility transformer. Chuck's saying, can you touch on the scenario where we're given the available fault current at the utility, but we do not have an idea what the X over R for a single line to, or the SLC, or single line to ground, which is required on the software? Okay, that's not a bad suggestion. Thank you. VCB means vertical conductors in a box, but not vertical in a closed box. No, so that's actually a good question. When we talk about orientation or configuration of the electrodes, we're talking about an enclosure that ostensibly at some point in time will be closed up. When it's closed up, the arc flash boundary, as long as it's has been installed and maintained per manufacturer's instructions, the arc flash boundary technically does not exist. So the problem is when we open up that door, or we open up that panel cover, we are exposing an individual to the potential for arc flash, and so it's vertical in a open box. Appreciate the difference. No, and so Chuck's saying, does the one line where we show the main circuit breaker, then a bus below it, does the software realize the main? So I have an example there, and the answer is yes. It doesn't. That's why we have to make some input to determine whether it's included or not. But well, I'll show it in just a second. Good questions. I appreciate that. Let me kind of jump into some of the examples. So what I want to show, just real quick, here's the intermediate calculation for arcing current and all the correction factors that are included, which makes it impossible to compare against the old standard. Here's the arc flash boundary, the intermediate calculations. And it's worthy to note everything's based on bolted fault current. but there's correction as many as 13 different correction factors any place you look. I think I kind of reiterate that 1584 recommends a dynamic assessment of arcing current over the life of the arc. In EasyPower, that's called integrated method. And so it integrates energy using the half cycle current during the first cycle. During the next 8 cycles, it will integrate using 5 cycle current. And then if the arc lasts longer than that 9 cycles, it will integrate the remainder using 30 cycle current. And I think I've got an example of that, or we can talk about that shortly. Now, the point I want to make is that EasyPower is closely coupled as far as the results between the short circuit module, the coordination module, and arc flash. And if we want the details on any particular parameter, it takes a little digging. That's why I think it's real important to understand the arc flash hazard report. So with that said, let's jump into EasyPower and we can kind of talk about some of these examples. And I think this first example is basically one that you have access on the tools called Protection 1. And let me kind of get rid of some reminders. And what I want to do is, again, this is a discussion. It's not a procedure on how to do any one thing specifically. But what I want to look at is what is going on with calculations for this particular bus. And before I do that, I want to go and look at see how the bus is set up. So this goes to Chuck's question. We're defining this bus as switchgear, and in the arc flash hazards, we're saying, okay, use a global definition for the arc flash calculations, and we have a couple user-defined specs here that we're taking something other than the default library values. So I'm going to undo those, and I'm going to go back and see how the calculations result on that particular bus. So let's go to short circuit. Now, I don't try to keep up with me. What I'm trying to do is just show you how I deal with some of this. I'm going to pick out this particular bus. I need to pick out some place that's not interfering with labels from the other elements. I'm going to fault the bus. Now I'm in short circuit. The fault conditions for this analysis are controlled by these little icons in the upper left. So consequently, we are looking at half cycle, 3-phase bolted fault. Well, so this is a worst case fault current. This shows me all the contributions, and the number on the oblique shows me the total available fault current. So that's my bolted fault current that's going to be passed over to the arc flash calculations. Now when I go to arc flash, this little Burning Man symbol at the top, now things have changed, and the control for the type of fault that we're going to be looking at are inside the short circuit options, arc flash hazard tab. Now these are going to control how the calculations are done. Now to Chuck's question, whether I'm excluding the main or including the main is on a global basis is controlled by this pull down here. So right now it says excluding the main. Let's just leave that for what it is. This is the control that determines the time element for when the calculations are done. So like we were looking at half cycle when we were in short circuit, let's go ahead and look at half cycle momentary now. And we're going to be looking at enclosed box distances. So now if I apply this, I can see the results here, but what does that do for me? Well, to look at the parameters, I'm going to arrange for arc flash. And this tells me that, okay, for that bus, the voltage, the tripping device, the upstream bus that's controlling the tripping device, the electrode configuration, all right, so this is basic out of the standard, the dimensions out of the standard, the gap out of the standard, the bolting fault current that was calculated, and then the bus arcing current. So right here, this is telling me at half cycle, the arcing current is going to be 15,000 amps as the bolted fault was 18.7, okay? But the branch fault current, this is what's actually doing the tripping time. So this is doing the integration, and this is doing the trip time. The branch bolted fault current and its response of to the response of the overcurrent protective device. Well, we already know this is R7. Well, R7 is this one in the primary. So back to Chuck's question, how come it's not using R8, which is in line? Now, the reason it's not using R8 could be it could be miscoordinated. It's like, okay, that's not such a good idea. How do I deal with that? Well, the first thing I want to look at are my short circuit options. And under short circuit options, we already said on a global basis, we're excluding the main. So what happens if I include the main and go back and look at these calculations? And what's kind of neat is I like to leave this open and look at the results as they change down here on my arc flash. So I'm going to apply that one change, and I see that, okay, in fact, R8 is now the tripping device. My branch arcing current is different because we're sensing in the secondary, and then the trip time looks like it's not that far off. So let's go ahead and talk more about this. So again, now we're looking at the secondary current for a bolted fault, the branch fault current, the branch arcing current. So again, this is the arcing current during that first half cycle, because if I go back and look at my options, we selected momentary current. Now, here's where the trick comes. We know at opening time, this is 83 milliseconds. This is the opening time for this breaker. And we can go back and verify that in a second. The arc time is a summation of the trip time and then the opening time, and that's over half a second. So the question is, why are we using momentary current? Because it changes after a cycle. So let's go back and kind of make a consideration there. So for starters, if I used 5-cycle current, let's see if that changes anything. Now again, I'm just talking a process that I go through to sort out what's going on. By using the 5-cycle current, the instant energy went down. The arcing time goes out a little bit, but my instant energy went down, and that's because we're integrating the 5 cycles at a lower current, and that lower current is 12.348. Okay, so half a cycle, half a second is still longer than 5 cycles. So let's go back to our short circuit options. Let's use the recommended integrated method, which is going to have a changing calculation time. And by faulting this, now we do get a more moderate instant energy. We do get a, and so this is a lower branch arcing current. So this is probably 30-cycle current. Now, when I say probably, I'm thinking, well, it started off the first cycle at momentary current, then it went for 5 cycles at interrupting current, and then the balance of the time, albeit half a second, was at the lower current. So how do I know what the actual instant energy is, or what the actual arcing current is? This is the one that bugs me, arcing current. So what's my reduced arcing current? Well, it's not showing here. It's showing me the arcing branch current, but it's not saying what the reduced arcing current is. Okay, well, this is where you talk about the coupling between the arc flash, short circuit, and coordination. If I go to coordination, plot, I'm going to plot the transformer, R8, and the bus that I'm trying to understand. Now again, this is just what I do to make sure I'm on the right page. If I fault this bus, I can single out just the one bus and fault it. Now again, I'm faulting at a half-cycle current, a 5-cycle current, or a 30 cycle current. Does that really help the equation? Well, it's changing slightly over all three ranges, but what I'm really concerned about is what's going on with the relay itself. So this relay, this tick mark, is a function of the way we set the relay up. If I go back and I look at the database for the relay, I see that it's set up to show me the 5-second interrupting tick mark. Let's go ahead and use the momentary tick mark and see where that shows up. And sure enough, it's higher, but it only lasts that long. Well, to cut to the chase, rather than trying to chase this down, the tool will tell me what the arcing current is. If I hover over the tripping device that's being cleared during the arc, and I right-click, it gives me the ability to insert the arcing current tick mark. And this little triangle that shows up at the bottom will show me that, in fact, we're using 100% arcing current, and where that intersects that curve, that's going to be the time that's being used for incident energy calculation. Did everybody get that? To me, this is a big deal. Okay, so back to Chuck's question. Okay, what happens if I'm going to define this breaker as I cannot exclude it? I mean, I have to exclude it because it's within the range of this bus work. So let's kind of go back. The reason I want to do this is show you how this is affecting sometimes and may or may not be important in the circuits you deal with. So let's go back to our arc flash setup. And I want to exclude the main. Now this is going to, so the difference is this is going to exclude it for the whole system. If I want to include it just for this one bus, I'd go down and do it locally. But right now I'm just looking at this, so yeah, let's include, no, let's exclude it, I'm sorry. I'm going to go back to fault the bus, look at coordination, look at the results for that particular. Well, now we're going to be tripping on this breaker. So let's include it in the plot. Okay, let's fault this particular bus. Now, again, we're still looking at half a second, and we think R7 is the tripping device. I'm going to right-click on R7, insert the arcing tick mark, and sure enough, it's still 100%, but it's going to be a completely different timeline than if we had the other one. Completely different. Looks like it's probably 10% off. Okay, so it does make a difference whether we're excluding or including. And if I go back to my arc flash hazard report, and look at this bus faulted, yeah, so my trip time now is quite a bit slower, and it even further it requires the need for integrated method. But my branch arcing current is now 2149 amps, which should be close to what I was showing there on that DCC curve. Okay, let's see if we got other questions. So, Robert, you're asking if I have a photo showing MCC. No, I don't. Um, I'll dig one up and send you. So these are in the eye of the beholder. And I guess my opinion is what you see and what you perceive is more important than what I can tell you. The significance is on a dry out breaker, most of the time when you have it drawn out, it's in the way of an arc that propagated on the bus behind it. And that is not encompassed in any of these calculations. So whether or not something is horizontal or vertical is somewhat muted by the fact that we're not considering objects in the way that could deflect incident arcing current. Okay, so we lost Chuck. Okay, so I'm not going to drill this into the ground anymore. I wanted to jump to the high voltage. This won't be quite as long. And sorry if it sounds like I'm stumbling around, but this is actually what I do when I'm trying to help someone debug their system. I had someone come in and saying, Jim, I've got my relay set up for 1800 amps. I'm seeing 4,000 amps on a fault current. Why isn't it tripping? So I saved this, or it got saved with my fuse open. Okay, let's go back and try this again. Okay. Well, the problem was he had a generator online for the whole time. And there it is. If we look at instant energy, while that generator's online, it goes through the roof. The instant energy goes through the roof. Well, the way we kind of deal with that is like, let's look at the arc flash hazard report. This shows on the main bus, the upstream tripping device is 9005, whatever that is. If I go in and find part number 9005, turns out it's a fuse, and it's, if we look at the current, it's still online at 9 amps. In fact, we saw that on our bolted fault branch current, that there was still 9 amps at the end of 1,000 cycles. So first of all, let's take this offline. Let's go back and recalculate our instant energy. And now we have an instant energy of 1.5 calories, and the tripping device is our relay that is just above it. But then at the same time, we look at this being a 25,000 volt system. So this is outside the range or the scope of 1584. Well, I would have known that if I had looked at the comment section, which says, okay, this is outside the range of that standard. What's going on? Well, again, we're in arc flash, so the rules are controlled by the short circuit options, arc flash hazard tab. And because it's outside of the range, EasyPower under the advanced modes gives this ability to do Ralph-Lee equations calculations or open air calculations. So if we apply Ralph-Lee, we get an instant energy of 7.7 calories. Now this is for a 3-phase open air fault. So that's not bad, but is it correct? If we go back in and look at our database, as we define this bus, it's defined as an open air bus. So in an open air condition or open air high voltage application, we have the need to do calculations on a single line to ground method or model. And so to invoke that, we go to short circuit, arc flash, SC options, advanced arc flash. Now instead of Ralph Lee, let's pick for an open air what we refer to as NFPA 70E 2009, which is a lookup table for high voltage open air single line to ground energies. And now by applying this, and faulting this bus, what we're seeing is a three-phase fault. We need to apply a single-phase fault, and by doing that, we can see our instant energy is a very modest half a calorie. And again, this is from a lookup table that was verified by the NESIC study and is sometimes referred to as the ArcPro results that was matched in the lookup table. So this is more accurately calculated now for a 25,000 volt system on the single line to ground, and our instant energy is calculated not using the 1584 model. Okay, any questions on that? So we have a webinar specifically for emphasizing how these are done and examples for using it so you can verify that you're getting the same results as we. And if you want to send me an email, we can do that accordingly. Okay, I've overrun my time. Appreciate you hanging in there with me. Any questions, by all means, shoot me an email. And good luck to you on your arc flash studies. Have a good day.